to thank the organizers for organizing this meeting. And so in this talk, what I'm going to describe is this work where we look at this Catchbond mechanism, how it manifests itself in terms of the transport properties of a single vesicle, which is driven by motors on cellular filaments. And this work has been done in collaboration with Anil Nair, who is in Pune University, Mithun Mitra, who is sitting here, and Sameep Chandel and Abhishek Chaudhuri, who are at ICER Mohali. So, yeah. So let me first begin with the cellular machinery that is involved in this process. So what you see here in this cartoon is a representation of the microtubule filaments. So transports inside the cell happens, so the filaments play the role of tracks on which material, like whether it is vesicle or some organelle, which is being carried on these filament tracks. And what carries them are these motor proteins like kinesin and dynein. And these filaments are within the cell. There are various classes of filaments. So you have this microtubule filaments, which typically are radially oriented within the cell. And apart from that, you also have actin filaments, which together makes up the transport machinery or these tracks that we are talking about. And so what these motor proteins do is that they hydrolyze ATP. And this hydrolyzed ATP gives rise to the activity of the motors, and which gives rise to this active transport. So basically this energy that they get from this ATP is converted into mechanical motion of these motors on these filament tracks. And these motors can actually, so one end of the motor is attached to this cargo, and the other end is attached to this filament tracks, and they can stochastically attach and detach to the filament. So in general, within the cell, a typical vesicle or cellular cargo is carried by many motors, and it can, so for unidirectional transport, what happens is that you have one cellular cargo which is carried by many motors of similar type. So when I say type of motors, I just mean that, so there are like this different classes of motor kinesin. So this filament tracks, this microtubule filament track has a polarity. And so these motor proteins are able to sense the polarity of this track. So depending on what kind of motors are involved, so for instance, if you have kinesin family of motors, they will walk towards the plus end of the filament. Similarly, dynein motors will walk towards the minus end of the filament. And like I'm repeating, so if in the case in general, you can have a situation where the cellular cargo is transported by these different kinds of motors, which will give rise in general to bidirectional transport of the cargo. But today for this talk, I'll be looking at unidirectional transport. By that I mean a vesicle which is being carried by one kind of motors. So just to summarize, so what are we looking at? We are focusing on the transport of a single vesicle, which is carried by many motors of the same type, and the processes which are involved are either kinesin or dynein motors, which are hydrolyzing the ATP and converting it into mechanical motion along these filament tracks. And you have this unbinding stochastic processes of binding and unbinding of these motors to the microtubule track. And the total number of motors, see the motors at one of the end is attached to the vesicle cargo. So that number remains fixed. It's only the number of motors which are attached to the filament which can change because of the stochastic binding and unbinding processes. And what we are interested in are studying the transport properties in steady state when this vesicle cargo is subject to a constant external load force. So how can we characterize it? We can characterize it in terms of, for instance, the probability distribution of these motors which are attached to a single microtubule filament, or for instance, the average number of motors which are attached to the microtubule filaments, and similarly, like effective unbinding rate of the vesicle from the filament track. And so, let's say if you have a kinesin motor, it likes to walk towards the plus end. Now imagine you apply a force in the opposite direction, a constant load force. And we want to study the transport properties. What happens to all these quantities? Like you can ask the question, what is the velocity of the vesicle? All these things, and the probability distribution or typical walking distances. Okay. So now specifically I come to what I mean by catchbonding in context of Dynein. So catchbonding is, so many of the binding processes for protein and ligands, So in general, the binding, the usual binding that we know is that, if there is a bound state and you apply some force, so in general, the unbinding rate increases with the force. So it likes to unbind if you are applying a force. And that's because, kinesin motors, in fact, fall under that conventional sense of binding, in the sense that you apply a force, so it basically lowers some kind of, if you look at the energy landscape, it lowers the barrier height, and so it's easy for it to dissociate. So this typically happens for majority of the cases, but in many contexts, in some contexts, and specifically also for Dynein motors, it behaves in a manner where you apply a force and the dissociation rate actually goes down with force, at least for certain range of force. And that is what I call as Catchbonding. And these circles are the data point obtained from in vitro experiments of a single Dynein. So this is done by this group of Ambrish Kunwar, then Gross and other authors. So what they see is what they found. So this, if you look, so K is the unbinding rate. So as they applied forces, which are of the order of piconewtons, so initially they see this rise, and then they see this fall up to whatever range of force that they have explored. And so we want to understand how to model that phenomenon of Catchbonding in context of Dynein. So that is the first thing that we would like to do. But finally, what is the manifestation? So this is the experiments for a single Dynein motor unbinding kinetics. We would like to study that if a vesicle is carried by multiple such Dynein, how are the transport properties affected by this kind of Catchbonding properties that have been observed. Okay. So coming to sort of the physical picture of how one can understand Catchbonding is that once you apply some force, so imagine that this protein-ligand binding, it has some landscape. If it so happens that it changes the conformation of the protein in such a manner that overall this potential minima goes down for certain range of force, then you have this Catchbonding effect, and that can be captured within. So there are various ways in which this Catchbonding is modeled in context of ligand protein binding. So one of this model is what is called the bond deformation model. So what it says is that you apply a force, so there is a deformation energy which can be expressed in this form. And so if you look at the unbinding rate, so if there is such a deformation energy is taking place, then it has two kinds of terms. So this is the usual slip term, which is just telling that, so in the absence of any deformation energy, it would have just behaved in a normal manner, in the sense you apply a force and the unbinding rate exponentially increases with force. Once you include this term, then there is a competition between this Catchbonding effect and the usual slip behavior. And in general, so what will happen if your deformation energy strength is sufficiently high, then you will have a behavior where for certain range of force, for initially small range of force, the unbinding rate will first decrease, and then eventually it will increase for higher ranges of force. Now this is a very general model. So let us now try to interpret the structure of the Dynein and what kind of Catchbonding model that we would like to have for Dynein. So this is again a cartoon of the Dynein, and so this is like the cargo, and this is the structure of Dynein. So what Dynein has are these AAA domains. So this is like a cylindrical conformation. So this is where ATP is actually hydrolyzed, and this hydrolysis, so there are 6 ATP hydrolysis sites. So in general, on application of some force, these AA domains are seen to contract. So they can contract, and the other end is, so this is the track. So this AAA domain are linked via this stalk to the filament. So this is just a blow up of what happens at the binding site on the filament, and one can think of some kind of lock and key mechanism that once you increase the tension at some value of critical value of the force, this Catchbonding effect sets in. So we just call it that there is some kind of threshold force beyond which this Catchbonding effect happens for Dynein, and so we can just represent it that so that bond deformation energy is given by some Heaviside function, theta function, and which sets in at some critical force Fm, and beyond that it has this form, and the overall unbinding rate just takes this form. So this is for modeling the effect of this single dynein. And in fact, if I go back to the last slide, so with the fit parameters, that is what we see. So once you take this form and then we obtain this fit parameter and try to fit it with the experiment, then it represents this basic behavior that has been seen in context of a single dynein. Now, correct. So the picture is that if I go to this slide, so imagine you are applying some force. So at some critical value of the force, so there is no catch-bonding effect which is taking place. It sets in when it sort of goes into this kind of lock conformation. So that was what I mean. And now that we have modeled this, now we ask the question that, okay, what is it? So how do we now statistically develop a theoretical model framework for analyzing what will happen when many such Dynein motors, which have this catch-bond effect, are going to affect the transport properties. So how we do it is like write down basically one-step master equation where we describe the state of the vesicle is characterized by the number of motors which are attached to the filament. And then you write the usual gain terms and loss terms. And then what we are interested in is really the steady state for this model. And so that will, steady state for the model is just, the usual thing. But we have to specify more things. I mean, one is, of course, we have to specify what are the form of the binding rates in a given state n. So given state n of the vesicle, by that I just mean that if the vesicle is in state n, that means small n number of motors are attached to the filament. And we also assume a linear force velocity relationship. That means if a vesicle is in a given state n, that is there are n attached motors, and you apply an opposing force, there would be a typical stall force, where at which force the vesicle will stop walking. So that is the stall force. And we also assume that the load that the vesicle feels, so that is divided among the motors. This is of course some kind of mean field like approximation, in the sense the load is shared between the motors. And then we, what we described just now, that we take into account the unbinding rate, and this unbinding rate has this form that I just described just now. And with that, now we try to see what comes out of it. So this is just for single dynein what I showed just before. And now we want to see that what is, for instance, if you have the total number of, capital N number of motors that are there are 5, again motivated by, in typical experiment, what is seen is that typically 4 to 8 dyneins are involved, at least for endosome transport. And we find out how, for instance, as a function of force, what happens to the effective unbinding rate of the vesicle. And it, qualitatively, of course, it has the similar behavior. What you see is this initial increase with force, then there is a regime where it decreases, and then eventual increase. If you look, for instance, the average number of attached motors, then that also, so it can in general go up and come down. And then for those specific fitted parameter values, you can also obtain the, the velocity of these motors. But now we can broaden this discussion to say this I have used the specific parameters that we have used. But we know that there are various classes of Dynein motors with different ranges of stall force, and presumably even different strengths of this catch bonding, which is characterized by this alpha. So once we explore this, this generic catch bond regime, and also in fact catch bonding is also seen for other motors like myosin. So we want to look specifically at this threshold force bond deformation model that I described, and the more bond deformation model in a more general context for different parameter regime. What we find is that, so various things happen. So typically how it affects is that, so because of catch bonding, in general what it tends to do is that, so if you apply, so this is the steady state probability distribution, which is peak. So it can shift the probability distribution towards, motor states, which have higher number of attached motors. But the most dramatic manifestation, so it affects, one can actually look at how it affects.
So your time is almost.
Yeah. But the most dramatic consequence, I would say, is how it can affect the force velocity curves. So here, like you can see, both for this TFBD model and BD model, that if you increase the force, there can be regions where you provide force and the velocity of this vesicle actually can increase. So this is one of the predictions that we are seeing. And in general, one can characterize this different. One can kind of come up with a velocity phase diagram which characterizes these different behaviors. Here we have characterized it in terms of number of humps that you will see in this force velocity profile that you get. And so with that, I would like to conclude, and thank you for your attention. We'll be glad to do it.
Any questions? Okay. So if there are no questions, then let us thank the speaker again.